The last thing that we're going to look at in this section is the derivative and the integral of a power series. Now, these are properties of functions defined by a power series. If you have a function and that function is equal to the sum from n equals 0 to infinity of a sub n times x minus c to the n, and it has a radius of convergence that's greater than 0, then on that interval of convergence, your function is differentiable and it's continuous, which means that you can find its derivative and you can integrate it. Now you might think, oh my goodness, that looks really scary, but it's not that bad. Remember what we said before? A power series just had it where it was x raised to a power. Well, imagine if I ask you to take the derivative of this. Well, that's not bad because the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, x cubed is 3x squared, etc. If I ask you to integrate, not bad either because we know how to integrate. We're integrating powers. So the beauty of a power series is that we're really just looking at an x to the n, and we know how to find the derivative of x to the n pretty quickly, and we know how to find the integral of x to the n pretty quickly. So just remember that the derivative of an x to the n is just n times x to the n minus 1, and the integral of an x to the n is going to be x to the n plus 1 all over n plus 1 plus c. So if your function is defined as a power series, it has a radius of convergence greater than 0, then its derivative is going to equal the sum from n equal 1 to infinity of n times a sub n times x minus c to the n minus 1. If you think about it, all we've done is taken this n and gone and multiplied the front like we do here. Take the n, go and multiply the front, and then raise it to 1 less. Raise it to 1 less. The integral of f of x dx is going to equal the sum from n equal 0 to infinity of a sub n times x minus c to the n plus 1 all over n plus 1, and then plus the constant of integration. So that we don't get it confused with the series, we put that constant of integration in the front. But if you think about it, it's the same thing that happens with the power rule for integrals, right? We take this guy, we add 1 to it. So we took this guy, we added 1 to it, and then we divide by that number, and we divided by that number. So what we're going to do is find the derivative and the integral of a power series, and then we also need to find the interval of convergence of the power series, its derivative, and its integral. Now, note, the radius of convergence that you get by differentiation and integration is the same as the original series. The only thing that differs is the endpoints. For example, here we got that our interval of convergence was 1/3 and 1. If we found the derivative of example 7, its interval of convergence would still be 1/3 and 1. We would just have to check those numbers in the derivative to see if they're included or not included. Same thing if we found the integral of example 7, its interval of convergence would be 1/3 and 1. The numbers don't change. What might change is what gets included and what doesn't get included. Therefore, you have to check the endpoints again. So let's look at example 8, where we find the interval of convergence of a f of x, b f prime of x, and c the integral of f of x dx. So let's start with a, because we already know how to find the interval of convergence of the function itself. That's going to be the easiest one. How do we do that? Well, we know that we use the ratio test. Looking at this real quick, we can tell we are centered at 5. Let's go ahead and use the ratio test to determine the interval of convergence for part A. The ratio test says to take the limit as n goes to infinity of the absolute value of, since it's the absolute value, I don't need to write -1 to the n plus 1. That's just going to be x minus 5 to the n plus 1 over n plus 1 times 5 to the n plus 1. And then I multiply it by the reciprocal of a sub n, which is just n times 5 to the n over x minus 5 to the n. Let's go ahead and expand and clean this up. So the limit as n goes to infinity of the absolute value, this is x minus 5 to the n times an x minus 5 to the first. I'm going to put it over my x minus 5 to the n. And then I have an n, then I'm going to put over an n plus 1. and then I have a 5 to the n. Then I'm going to put over the 5 to the n times 5. And I'm just putting them this way so it's easier to see what cancels. So your x minus 5 to the n's will cancel. Your 5 to the n's will cancel as well. And all you're left with is an x minus 5 over 5. And then for your n's, an n over n plus 1. Well, the limit as n goes to infinity of the absolute value of x minus 5 over 5 times n over n plus 1. Well, the n's are just n over n. And we know that that guy is going to reduce to 1. This ends up being the absolute value of x minus 5 over 5. Well, we ended up with an x, so I know I have to set this guy less than 1, solve that inequality, and then check my endpoints. So I'm going to do all of part A up here on the top, and then we're going to go to part B. So I'm going to move over to the right-hand side over here. So the absolute value of x minus 5 over 5 has to be less than 1. Then that becomes negative 1 less than x minus 5 over 5, and that's less than 1. Multiply everything by 5, and you get negative 5 less than x minus 5, which is less than 5. Add 5 to all three sides, and you get 0 is less than x, which is less than 10. So if you think about it, you are centered at 5, and you get to move to 0, and 10, so that radius of convergence here is 5 units. Now we have to check the endpoints. In order to check the endpoints, we have to put it back into our function. So we have to go back into this series right here. So let's go ahead and check x equals 0 and check x equal 10. For x equal 0, you're looking at the sum from n equal 2 to infinity of negative 1 to the n plus 1. If I plug in a 0, that becomes negative 5 to the n all over n 5 to the n. Well, negative 5 to the n is just negative 1 times 5, so I can rewrite this guy right here as a negative 1 to the n times a 5 to the n. If I do that, I'm looking at the sum from n equal 2 to infinity of negative 1 to the n plus 1 times a negative 1 to the n times a 5 to the n all over n 5 to the n. Now I notice that my 5 to the n's will cancel, and then in the numerator I have negative 1 to the n times negative 1 to the n. When the bases are the same and we're multiplying, we add the exponents. So that becomes a negative 1 raised to the n plus 1 plus n, which is 2n plus 1. And we've already talked about that. If it's 2n plus 1, what that meant is that we no longer alternated, and that was just an odd number. So we factored out the negative 1 because this exponent here is always going to be an odd number, and if we're raising negative 1 to an odd number, we're always negative 1. Pull out the constant multiplier and then see what's left over. Well, all we are left with is a 1 over n. What do we know about 1 over n? It's a p series. P is equal to 1, therefore we know this guy diverges. So we're done with x equals 0. Let's check x equal 10. Now we're going to plug in a 10. If I plug in a 10 here, we're looking at the sum from n equal 2 to infinity of negative 1 to the n plus 1, and that's going to be 10 minus 5, which is just 5 to the n all over n 5 to the n. Well, the 5 to the n's will cancel, and all you're left with is the sum from n equal 2 to infinity of negative 1 to the n plus 1 all over n. Well, negative 1 to the n plus 1 all over n, this guy here is an alternating series. And if you're an alternating series, you can use the alternating series test. The absolute value of a sub n is 1 over n. So what is the limit as n goes to infinity of 1 over n? Well, that's equal to 0. First part of the alternating series test has been met. The second part is a sub n plus 1 less than or equal to a sub n. Well, we just did that earlier, and we know that to be true. Therefore, what do we know? That this is going to converge by that alternating series test. For part A, when we're looking for the interval of convergence of your function, the interval of convergence, remember it's going to be the numbers 0 and 10. At 0 we diverge, so we don't include it. At 10 we converge, so we do include it. Let's do part B. Part B wants the interval of convergence for f prime of x. In order to find the interval of convergence for f prime of x, I first need to find f prime of x. So f prime of x, given that your function is this guy right here, is actually not that hard to find. Remember, what you're doing is just the power rule. So it's still the sum from n equal 2 to infinity. Negative 1 to the n plus 1 doesn't have an x. Since we're taking the derivative with respect to x, it's a constant multiplier that multiplies along. This guy here has an x, so I use that power rule. My n will go and multiply the front, and then I take my x minus 5 and I raise it to 1 less, n minus 1. And then the denominator doesn't have an x, so it's a constant multiplier which multiplies along. Well, now I notice that my n's cancel, therefore this guy here is just going to equal the sum from n equal 2 to infinity of negative 1 to the n plus 1 times x minus 5 to the n minus 1 all over 5 to the n. And now what I need to do is I need to determine what the interval of convergence is. Well, the nice thing is that I don't have to do the ratio test again. I just have to check the numbers 0 and 10. So I have to check 0 and 10 to see if I converge or diverge. The numbers don't change. These numbers are always going to be the same, no matter if we're taking the first, second, fifth derivative, integrating once, twice, keep going integration. That doesn't matter. It's still always going to be 0 and 10. What differs is whether they get included or not included. So the endpoints might differ. That's it. Let's go ahead and check x equals 0. So if I check x equals 0, I'm plugging in a 0 in place of my x here. That means that I'm looking at the sum from n equal 2 to infinity of negative 1 to the n plus 1. If I plug in a 0, that becomes a negative 5 to the n minus 1 all over 5 to the n. If I clean that up, I know that negative 5 to the n minus 1 is just negative 1 to the n minus 1 times 5 to the n minus 1. So we'll say negative 1 to the n plus 1, and then negative 1 to the n minus 1, and then 5 to the n minus 1. And this is all over 5 to the n. Well, the bases are the same here, so we add the exponents. N plus 1 plus n minus 1 is just 2n. So that becomes negative 1 to the 2n. And then this becomes 5 to the n times 5 to the negative first, all over 5 to the n. The first thing I realize is my 5 to the n's cancel. The second thing I look at is 2n. So 2n is the formula for an even number. So this guy here is always going to be an even number. So if I take negative 1 and I raise it to the second power, it's positive. To the fourth power, it's positive. To the sixth power, it's positive. So if I raise it to an even number, it's always positive. So I don't have an alternating piece here. I don't even have a negative 1 to the 2n. That goes away because I'm always really multiplying it by 1. We can rewrite this guy as the sum from n equal 2 to infinity. This guy here, remember I said, is really just a 1 because a negative 1 to the 2n is just a 1. And since this has a negative exponent, if I move it to the denominator, I have the sum from n equal 2 to infinity of 1/5. So what happens here? Well, this is not a known series because it's not a p series, it's not geometric, and it's not telescoping. So let's try the nth term test. What is the limit as n goes to infinity of 1/5? Well, that's equal to 1/5, which is a number that's not 0. Therefore, by that nth term test, we diverge. So we know that we will not be able to include 0 in our interval of convergence for the derivative. Now let's check the other endpoint. Let's check x equal 10. If I check x equal 10, instead of writing this x here, I'm going to write 10. And that becomes the sum from n equal 2 to infinity of negative 1 to the n plus 1. 10 minus 5 is just 5 to the n minus 1, all over 5 to the n. Well, that becomes negative 1 to the n plus 1, and that's 5 to the n times 5 to the negative first, all over 5 to the n. My 5 to the n's cancel, and then that's just the sum from n equal 2 to infinity of negative 1 to the n plus 1, all over, this has a negative exponent, let's move it to the denominator, which is 5. Well, that's an alternating series. Since it's an alternating series, I can try the alternating series test. First thing you do is take the absolute value of a sub n, and that's just going to be a fifth. But wait a second. I just showed that this guy here diverges, right? It diverges by the nth term test, so I know it's going to fail the alternating series test. Therefore, I know that this guy also diverges. Why? Again, you just found it on the series that you looked at to the left. You don't have to do the test again if you just determine that it's going to diverge. Therefore, we know that the interval of convergence for part B here, remember it was the same numbers, 0 and 10, but they both diverge, so neither is included in the interval of convergence. And let's do the last part. Let's do part C, and part C has us finding the integral. Since I can't see the function, I'm going to go ahead and rewrite the function again so that we can use that to integrate. Remember, the given is just the sum from n equal 2 to infinity of -1 to the n plus 1 times x minus 5 raised to the n all over n times 5 to the n. If I'm integrating this, the integral of f of x is going to equal, remember we always start off with that constant of integration so we don't get it confused with inside our series, and then it's the sum from n equal 2 to infinity of. Now this doesn't have an x, which makes it a constant multiplier. It multiplies along. This does have an x, so it's just that power rule. We add 1 and divide by that number. So I add 1, that's an x minus 5 to the n plus 1, and then I divide by n plus 1. The bottom is just a constant multiplier, so then I write the rest of it down, n, and then 5 to the n. So I end up with the integral of f of x dx is c plus the sum from n equal 2 to infinity of -1 to the n plus 1 times x minus 5 to the n plus 1 all over n plus 1 times n times 5 to the n. Now let's find that interval of convergence. Remember, it's still 0 and 10. Just got to figure out, do I include them or do I not include them? Let's check those endpoints. I'm going to start by checking x equals 0. So if I'm plugging in a 0 into this, we're looking at the sum from n equal 2 to infinity of -1 to the n plus 1, and this becomes -5 to the n plus 1. And since it's a -5 to the n plus 1, we're just going to go ahead and write it as a -1 to the n plus 1 times a 5 to the n plus 1, just to make this simplification a little easier, because we know that that -5 to the n plus 1, we'd split into 2 in the next step anyway. And then all over n plus 1 and 5 to the n. Well, now I have -1 to the n plus 1 times -1 to the n plus 1. When your bases are the same, you add your exponents. N plus 1 plus n plus 1 is 2n plus 2. So we're looking at the sum from n equal 2 to infinity of -1 to the 2n plus 2, and then this guy splits up as 5 to the n times 5 all over, and I'm going to write this guy first, n, and then n plus 1, and then a 5 to the n. And the 5 to the n's definitely cancel, and then I look at this guy right here, 2n plus 2. Well, I know that 2n made something an even number, so if I take 2n, which is an even number, and I add 2 to it, it still stays even. So this is still an even number. Since it's an even number, we know that that -1 to the 2n plus 2 goes away, because that's really like multiplying by 1. Therefore, we can rewrite this series as the sum from n equal 2 to infinity of just 5 over, and I'm going to go ahead and distribute the denominator, n squared plus n. Now I have to figure out, does this series converge or diverge? Well, I'm not sure. It's not a known series, so it's not a p-series, it's not geometric, and it's not telescoping. So let's do a comparison. What does it look like? Well, if we look at it, it looks like a 1 over n squared. So let's compare it to a 1 over n squared. What is 1 over n squared going to do? It's a p-series where p is equal to 2, and I know that it's going to converge. So let's do the limit comparison test. The limit as n goes to infinity of your given is this guy, 5 over n squared plus n, divided by your known, or times the reciprocal of the known, so times n squared over 1. So that becomes the limit as n goes to infinity of 5n squared over n squared plus n. Well, that's just a 5n squared over n squared if we're looking at those leading terms. And if we reduce that, that just becomes 5 because 5n squared over n squared will reduce to 5. So you're looking at the limit as n goes to infinity of 5. Well, that's equal to 5. Well, 5 is a finite positive number. Therefore, by that limit comparison test, you converge. Now check the other one. Check x equal 10. Plug 10 into this x right here. So we're looking at the sum from n equal 2 to infinity of negative 1 to the n plus 1. If I plug in a 10 there, that's 10 minus 5, which is just 5 to the n plus 1, all over n plus 1 times n times 5 to the n. Clean this up. Well, that's a 5 to the n times 5 all over n times n plus 1 times 5 to the n. Those 5 to the n's will cancel, and you're just looking at the sum from n equal 2 to infinity of negative 1 to the n plus 1 times 5 all over, if I distribute here, that's n squared plus n. Well, this is an alternating series. Since it's an alternating series, I can use that alternating series test. First, I take the absolute value of the series, and the absolute value of a sub n is just going to be 5 over n squared plus n. But wait a second, I don't even need to do the alternating series test on here. Why? Because I already know what happens to this series. What happens to it? It converges by the limit comparison test. We just did the test for it on the left. Don't do the test again because you've already done it. We know that this series is going to converge. Since it converges and we were trying to find the interval of convergence for part C, we know that the interval of convergence, remember it's the same two numbers, 0 and 10, we converged at both, we'd have brackets for both. That's it for power series.